Thank you. So this is a joint work with my students Matthew and Helen Chen, and we are going to explore how to use erasure coding in in-memory key value store. So we have seen a lot of examples, use cases of in-memory key value stores that has been widely deployed for scalable and low latency access. There are many examples of that. However, if we deploy in a distributed manner, failures will become a problem. So the question is, how do we protect the data in the in-memory KV store from the failures? Of course, usually these in-memory KV stores are usually used as a cache, so you may go to the secondary storage to recover the data, but the overhead could be huge. So the question is, can we just keep redundancy directly in the memory? So the most intuitive approach is to apply replications, but the thing is, that will be introduce high storage overhead. Even though we can buy a lot of servers with RAM, but still, it's not storage efficient. So another approach, which has been used by some systems like RAM Cloud, is can we just store the redundancy in secondary storage, such as hard disk? And the problem we think is actually that will introduce high latency to access these replicas, especially when we issue degraded read, in which we want to read the data, redundancy data from the secondary storage in order to recover the data. So the overhead could still be huge, especially during the failure recovery. And here we try to see if we can use erasure coding in the in-memory KV stores. And erasure coding has an advantage of being storage efficient. It is provably introducing minimum data redundancy. And we want to look at if it's possible to just keep the redundant information entirely in memory so that when we do the recovery, we don't need to go to secondary storage, but we go to other available servers to recover the lost information, especially under failures, or maybe not the failures, but like stragglers, which has poor performance. So we can just, instead of accessing the stragglers, we can just go to other available servers for the data. Now let me give you a brief overview about erasure coding. So the basic idea is there are two parameters, k and n, where n is greater than k. So we divide the data into k data chunks and we encode them into additional n minus k parity chunks. This encode could be based on like linear combinations. And each collection of these n data parity chunks is called a stripe. So typically a storage system has many stripes that are independently encoded, and will distribute each stripe to n different nodes or servers. And the nice property about erasure coding is the fault tolerance, meaning that nk of n nodes can recover the file data with minimum amount of redundancy. And the redundancy here we define as n over k. Typically, we want this to be less than 2, because if it's greater than 2, that is like replication. So we want to have something like 1 point something for the redundancy. Now, there's no free lunch for using erasure coding. There's a high performance overhead, particularly in data updates and recovery. So there are many solutions proposed in the literature, either by proposing new erasure code constructions or proposing some new schemes that work for general erasure codes. But the thing is, when we deploy erasure coding in in-memory KV stores, we face additional challenges. First thing is, we find that in real workloads for the in-memory KV stores, the object size is usually very small. How small it is, usually these keys and values could be as small as just few bytes, maybe 2 or 3 bytes for the values. That has been shown in a Facebook field study in Symmetrics paper. And typically, erasure coding is used for encoding large objects. So you have one object, you chop it into k chunks, and then you do the encoding. But the thing is, if you just have values of 2 or 3 bytes, it's not quite feasible to do erasure coding at all. And also, because of this small size object, and when for in-memory KV stores, we issue the decentralized request. We don't want to go to the metadata servers to look up the information where to store the data. We just want to use something like, for example, consistent hashing to map the object to a server. But the thing is, when we deploy erasure coding, we have to maintain the data consistency between the data and parity chunks. For example, when you update the data chunk, you also need to update the parity chunk. So here comes our contributions. we built a system called MemEC to realize a high availability erasure-coding-based in-memory KV stores for small objects in particular. And we aim for 3 goals: low latency access, fast recovery, and also storage efficiency. And we propose a new model for the encoding of small objects, which we call the Encoding Model. And based on this model, we propose some mechanisms to ensure graceful transitions between the normal mode when there's no failure and degraded mode, which has failures. And then we do a lot of test-bed experiments on our prototype using the YCSB workloads. Now, let's take a look at what is the existing data model being used by the existing KV stores. And the most widely used approach is just by replications. So typically, an object consists of 3 fields: the key, value, and some metadata describing the object, and also the reference that points to this object. We don't consider how exactly this information are being laid out in the server. This is not the concern here. But the key point here is that this information will be replicated across multiple servers. So if you would expect that the storage overhead could be quite large. So the question is, can we reduce the storage overhead? And actually, some approaches have been proposed for the in-memory KV stores. The idea is it assumes the value size is sufficiently large. So we apply erasure coding to the values only, while for the key metadata and the reference to this object will be replicated. Because the value size is large, so the storage efficiency should go to the expected redundancy. The optimal redundancy basically is n over k. And actually, it has been used by some in-memory KV stores, such as LH*RH, which was proposed back in 2005. And recently, there's a paper, there's a work called Systor, which was proposed in FAST 2016, also using this type of ideas. But the thing is, the assumption here is the value size needs to be large enough. So if the value size is very small, like as small as 2 or 3 bytes, so what we can do? And what we do here is we propose an all-encoding model. The idea is to apply the erasure coding to the objects in entirety. Basically, it means that the keys, values, and metadata are all erasure coded. And then we design some specific structures for the references to reference these data chunks and objects to limit the storage overhead. And I'm going to give you more details about how this all-encoding data model is designed. First thing is, we will divide the storage as a collection of chunks. Here, we use fixed size 4 kilobytes as the units for the erasure coding. So these data chunks or parity chunks will be stored in different servers. And for each server, there will be 2 index tables which stores the references to the chunks and also to the objects. And inside the chunk, for example, for the data chunk, we will try to append the metadata key value as an object to one of the chunks. And these chunks will be uniquely identified by a chunk ID, which is 8 byte long for now, for the chunk identification in the server. I'm going to talk about how we design the chunk ID in a moment, but the thing is, we try to pack everything into a chunk. So when a new object comes in, we will append this information to the chunks. And when the chunk size limit is reached, we will seal the data chunks. And the sealed data chunks later will be encoded to form the parity chunks that belong to the same stripe. I don't go through the details in this talk, but you can refer to the paper. The thing is how we generate this coded information. So the main idea is the following. When we write a data object, we write it to one data server, and at the same time, we write the data objects to all the parity servers. When this data chunk is sealed, this data server will notify the parity servers that, hey, please update the parity chunks based on the data objects that you have received. And the parity server will add these data objects, merge the information into the parity chunk. And in erasure coding, there's a nice property that each parity chunk is in fact in linear combinations of the data chunks of the same stripe. So that means that you don't need to collect all the data chunks to form the parity chunk, but instead each parity chunk could be updated incrementally. So you have a new data chunk, you can add it to the parity chunk based on linear combinations. So in this case, that will not introduce a large overhead when we're encoding these parity chunks. For details, you can refer to the paper. But the thing is, we'll form these chunks, we'll seal the data chunks when it's full. And also, one thing I would like to point out that when I seal the data chunks, this object could still be updated as long as the value won't roll beyond the value size. We allow the in-place update for the object as long as the value size doesn't change. That could be one limitation for now, but in fact, even though this data chunk is sealed, we allow this object to be updated. And also, we use two index tables to refer to the key and also refer to the chunk, so that I know where this object is stored and where the chunk is stored. And we need this information because we also need to we need to know how to update the parity chunk when we issue an update. So this index tables basically is like a hash table. One thing we realize is we can leverage some existing hashing scheme based on Kuku hashing. Sorry for a typo here. Based on the Kuku hashing, the main idea of Kuku hashing is it eliminates a lot of extra pointers to resolve the hash collisions. So it allows us to pack all these references into one hash table. And one thing I would like to emphasize is you don't need to store the key information in the hash table because the data chunk inside, the object inside already has the key information. So to resolve the hash collision, all you need to do is just go to the object and check the key value. And then we just store this index in each server. And one thing is you don't need to create additional redundancy for these indexes because the chunks themselves already provide the redundancy information. So when something is lost, you recover it, you can reconstruct the hash tables from the chunks. Now, the thing is, we also need to store additionally the key to chunk mappings for the failure recovery. But somehow these mappings could be stored in secondary storage and you only retrieve them when doing the failure recovery. So that part will not affect the memory storage overhead. So for the chunk ID, this actually has three fields. The first one is the stripe list ID. Basically, it defines the set of data and parity servers for the stripe. It is determined based on the key input. How to find the stripe list, you can refer to the paper. Basically, we bootstrap a list of servers, multiple lists of servers, and you can pick one stripe list based on the key. For the stripe ID, basically the server will maintain a local counter, and when this data chunk is sealed, it will increment the local counter. So it has the unique stripe ID. And also, we identify the chunk position from 0 to n-1 to identify where the chunk belongs to in the stripe. And the chunks for the same stripe will have the same stripe list ID and the same stripe ID. So we do some analysis to understand the redundancy overhead. We fix the key size and also the NK equals to 10.8. X-axis is the value size, Y-axis is the redundancy. Actually, we find that for the replications here is the 3 times replication, but in fact the redundancy is much higher than 3. It's because of the references. So when the value size is very small, actually the difference between the redundancy is quite huge. Although when the value size, when it becomes large, for both the hybrid and all encoding, it will converge to n over k. But the thing is, for small value size, we'll have an advantage of limiting the redundancy. Same thing happens for other key size, and actually in the paper we also studied another set of NK to show that our approach has limited redundancy. So this is our architecture we built. Basically, we support set, get, update, and delete requests. The proxies will issue decentralized requests to the servers, and we have a coordinator here. But I would like to point out that it's only involved in the normal I/O path during the degraded mode. And in the normal mode, when there's no failure, everything is decentralized. So the thing is, but when failures happen, the process needs to know where the data should be sent to. Let's say I want to write it to a server, but this server fails. I need to redirect the request to another server. So that means that I need to need the coordinator to help out, basically to redirect the request to a redirected server. We call them the degraded request. And when we move from the decentralized to degraded request, we need to ensure the data consistency by reverting any inconsistent change or replay any incomplete request. And I'd like to point out that the requests that do not involve the failed server will still remain decentralized. It only affects those requests that involve the failed server. And the rationale here is degraded mode could happen, but compared to the normal mode, it won't happen for a lot of time. So even though we involve the coordinator in the degraded mode, it should not affect that much, because for most of the time, normal mode is still the common case and is still decentralized. So the coordinator will maintain the server state for each server. Basically, what it describes is we use the two-phase protocol when there's a failures happen. So when the coordinator detects a server failure, it notifies all the process to finish all the decentralized requests to revert any inconsistent change that's in the intermediate state. And the process will notify the coordinator when finished, and the coordinator will notify all the process to issue the degraded request by the coordinator in the degraded state. And we use the atomic broadcast to ensure that the state transition moves correctly. We do some evaluation. We have a testbed with 1 gigabit Ethernet. We also try out 10 gig Ethernet, and the performance is quite similar. And we studied using the YCSB benchmarking. We did quite a lot of experiments, which you can refer in the paper. I would just like to highlight the case when failures happen. So what we do here is we pick one server as the failed server. What we do is we ingest some artificial delay to delay the request from the proxy to the server. Here we introduce a delay with normal distributions, which mean 2 milliseconds and 1 millisecond of standard deviations. And what we observe is for the normal request, it would take like 2 milliseconds. And if you don't do anything, just let request access those failed server. You can still access it, but with long delay. That will go to 4 milliseconds. But if we allow the degraded handling be enabled in our system, we'll drop it back quite close to the normal request. And this is the failure case before we load the data. And after we load the data and we trigger the failure, we also study the latency. And for workload A, which is in YCSB, is update. 50% of them are updates, 50% are guess. We find that our degraded request still quite high compared to the normal request. The reason is because the updated request actually you need to resolve the consistency. So actually, it also affects the get latency later. But for the C workload, which is purely get, and the degraded request is actually quite close to the case in normal mode. And we also studied the state transition overhead from the normal to the degraded state. Basically, without request, the single failure is like 1.74 milliseconds. And with request, that will be 4.77 milliseconds because we need some time to revert the parity updates. When the degraded mode go back to the normal mode, without the request, it only takes 0.91 milliseconds. While with request, because we need to migrate the data from the redirected server back to the restore server. So it's quite high, but it's still within 1 second. So it's 600 milliseconds. So to conclude, we propose a system called MemEC with 2 key designs: how to support the small objects and how to support the graceful transitions between the normal mode and the degraded mode. And our prototype is currently open source, which you can download and find it out, test it. And there's still a lot of future work, such as right now we build a system from scratch, but the data models themselves actually could be integrated into existing system like MemEC, Memcache, and also Redis. So it's interesting to see how to improve the existing system. And also, we don't we could explore new consistency mechanisms to improve the performance as well. So thank you, and I appreciate your questions and comments.
Your delay numbers, I assume, are under no load. In other words, just a simple request, see what happens.
Yes.
Because when you go to higher loads, I think you will see something severe happening, which is due to the fact that the amount of work that needs to be done in degraded mode or for update is, the work is done in parallel, but it still needs to be done, which means that the total load you can take throughput will decline by a factor of the amount of work that needs to be done, unrelated to the latency. And then when you take the usual throughput delay curves, you will see that to incur reasonable delay, you have to operate at much lower throughput than you could without this system. So the zero load delay, I accept your numbers, but when you want to work in a heavy loaded systems, the penalty will be much worse.
I agree. Yeah, I agree. Yeah, that could be the point. Thanks.
Another question?
So, before you do erasure coding, you form the chunks. So key value items and chunks are packed.
Yes.
And I just wondering how actually you carry out this delete operation, which is going to be composed in chunk.
What we do now is just like update. We mark this as so we just mark the object as invalid, and also update the corresponding parity chunks. You can think of, you update the object like zeros value, and then you also update the parity chunks for consistency. And later we need to do the garbage collections. Here we don't show the results, but yeah.
Yes, that you have not say more details about garbage connections. Is that going to be very expensive, or how you are going to schedule this to see as I use? So if these all scattered around across these chunks.
That takes some overhead. Yeah, I agree. That will take some overhead, especially when you compact these chunks. And I agree. We did some experiments, but definitely that we can improve that. And right now we don't explore any workload characteristics to improve the garbage collection performance. But there's a lot of work about this along this line. Yeah.
Have you considered if you can reduce the overhead during the degraded mode? Because it seems as if you want to scale, as you get larger clusters, you're going to have more failures. And in the degraded mode, things slow down a lot. And then you might have another failure before the first failure is finished.
Yes.
So
And
I'm wondering what your thoughts are about that.
so this is one major design assumption we make is normal mode is the common case, and we go by the coordinator in the degraded mode. The coordinator will be the bottleneck for sure if your degraded mode lasts for a long time. I think one way to address this, I didn't know the details, but maybe to resolve the may take a weaker consistency guarantees. Maybe that's one way to handle that. Yeah, that's what I can think of for now. Yeah. Yes.
Do you have any figures showing how the difference between degraded and undegraded grows or goes down as you increase the number of replicas servers for process? Would it scale better or worse?
The sensitivity.
We don't have these numbers. We just limit to trend node testbed. Yeah, we don't have these numbers.
Any other questions? Okay, I have a question. You have an intricate, system for the input work, and there are so many parameters. Have you tried to come up with an analytical model to have the overhead, modeled so you can do some decisions based on that? Have you looked into it?
What types of parameters that we choose?
Yeah, and based on those parameters, can you have like a model to decide on the overhead that you will suffer?
So basically, the equations can take some different parameters. You can plug in n, k, or even the reference size, the utilization of the hash tables. You just plug in the different parameters and you can try it. We have the equation form as a general to find out for the general case.
For the general. Okay, there are no other questions. Thank you.